Hi everyone. In this pre-lecture video I want to go a little bit further in our description of prototypical system as a container of ideal gas. We've talked already about state variables which describe that system, pressure, volume, and temperature. But what I want to talk about today is energy. So I want to talk about these new concepts about work, heat, and internal energy. And we're going to start by doing a big picture discussion of conservation of energy, and then try to describe what those variables work, heat, and internal energy mean. So here's the outline again. Talking about energy now with regard to thermal systems. You all know that the total energy in the universe is constant. We have this amazing fact called conservation of energy, meaning that I can't create or destroy energy, but it can change forms. Right? So the total amount of energy in the universe, for some mysterious and not well understood reason, is the same. It does not change over time. If you want to think about this more schematically, basically, you know that the total amount of energy in the universe does not change with time, but luckily we don't have to study the entire universe when we're doing a problem. So we divide the universe into two pieces, which we call the system and the environment. And this boundary is arbitrary. You know, what you call the system and what you call the environment is really up to you, but your analysis will change depending on how you've defined the system. Okay. The total amount of energy in the universe is fixed, so no energy can be created or destroyed, but the system's energy can change if it borrows energy from somewhere else in the universe. So the system and the environment can exchange energy back and forth. And therefore, I can change the energy of the system by transferring energy into it or removing energy from it. I haven't created or destroyed energy overall in the universe. I've just moved it from place to place. If you want to write conservation of energy in an equation, it's basically expressing that idea. So the change in energy of the system is equal to the amount of energy that is transferred in or out. So change in energy of the system is equal to the energy that's transferred in or out. So this delta is always the final energy of the system minus the initial energy of the system. And this is equal to the energy transferred in or out. Of the system. Okay, so there's my my expression for conservation of energy. Now we have to think about what kind of energies can a system have. Okay, so this is going to be a bit of review. Hopefully you know there's kinetic energy. And this is going to be energy associated with macroscopic motion. So that's motion that I can see by eye, right? Visible with the naked eye. And then we've got potential energy, which is energy associated with macroscopic position. So mgh, right? How high is the object? That determines its gravitational potential energy. 1/2 kx squared. Where is the mass on the spring? That determines its gravitational, its elastic potential energy. If I just had those two, this again is review, you would have my conservation of energy equation would look like this. Change in the energy of the system is equal to the energy transferred in or out. And so I would have change in the kinetic energy Ke plus the potential energy, Pe, is equal to the energy transferred in or out. If E transfer equals to 0, then kinetic energy plus potential energy of the system does not change. So this is an example of something that you've seen before, probably a mass on a spring. So initially, it has some gravitational potential energy and some elastic potential energy because the spring has been stretched by hanging the mass on it. The total energy is found by summing up those two bars there. If I grab the spring and I stretch it and let it go, let me click play here. It's in slow motion here. You'll see now at different places, the system has different amounts of kinetic energy and potential energy and elastic potential energy. So at the center of oscillation, it has a high amount of kinetic energy, and then when it's higher, it has a higher potential energy due to gravity, and so on. But the sum of those always adds up to the same number because the energy is conserved. No energy is being transferred in or out. It's just changing forms between kinetic and potential here. Now in this course, we're going to have a different kind of energy, which you haven't seen before, which is called internal energy. And I'm going to say this is energy associated with microscopic motion and or interactions in a system. And what you should have in mind is that basically this is going to be what we call thermal energy. Okay. So this internal energy is a new kind of energy, and it's given the it's given the variable U. So this one is Ke, kinetic energy. This one is potential energy. And this one is called U, internal energy. And that's the thermal energy of the system. So if I include this other kind of energy, I need to modify this. Right? I don't have just kinetic and potential. I have change in kinetic energy plus potential energy plus the internal energy is equal to the energy transferred in or out. Okay, so we're going to have here delta K E plus the change in potential energy plus the change in internal energy or thermal energy is equal to the energy transferred in or out. And generally I'm going to ignore this because this is covered in mechanics classes. We'll usually ignore it. So that's, again, remember, macroscopic motion, like a ball flying through the air, something moving which you can see by eye. Now, I know some of you already know that the internal energy of a gas is actually the kinetic energy of the molecules moving around. But I'm not going to call that kinetic energy. That motion, the microscopic motion of the gas molecules, which you can't see with your eye, is this part of this U. That's the thermal energy of the gas. Okay. Of course, U is an energy, so the units of U are joules. And the other thing that's important to note is that U is a state variable. It's a property of the system. So the system has internal energy. It has thermal energy. Remember, a state variable is something that you have, right? I have a pressure. I have a temperature. I have a volume. I have an internal energy. It's a property of the system. Just to remind you, a joule is a kilogram meter squared per second squared. And remember, in this course, there's an important difference between the small variables and the capital variables. So if I write the small u, that's going to be specific internal energy. And the small u is always per mole, right? Remember, the small v was specific volume. That's volume per mole. The small u is the capital U divided by the number of moles. So the units of the small u are going to be joules per mole. Okay, so in this course, we're mostly going to be focused on this part here. Going back to this simulation, if I let this go, it would run forever. The total energy of the system never changes. But you know in the real world that never happens. You know that in the real world, if I had something like this, it would eventually stop. So I should make this simulation a little more realistic by turning on this thing called damping. I'm going to add some damping to the system. And damping is sort of the effect of friction and also internal forces in that spring. And as this is going on, you're noticing a different kind of energy is showing up here, which is E therm. That's the U that we're talking about, internal energy or thermal energy. And maybe I'll put it in normal motion, so let it go. You'll see eventually it will settle down. And the total energy is the same as it was before, but now I have no kinetic energy, whereas I started with some kinetic energy, right? So where did that energy go? You know the energy can't be created or destroyed. And so where that energy went is to something I can't see with my eye, but if I measure the air around this mass, or I measure the temperature of this metal spring, it would have gone up a little bit. And so there is still thermal energy, internal energy in this system, which is showing up at this red bar here. Okay, so the total energy changed form from kinetic and potential into thermal energy, but it's still there, right? It's just maybe not visible with the eye. Now let's talk about how I can transfer energy into or out of a system. We've talked about the kinds of energy a system can have, kinetic, potential, and internal energy. Now what's going on this side? How do I transfer energy into or out of a system? There's two ways that we're going to be focused on. And the first one is probably a review again from your earlier courses, which is how do I change the energy of a system by pushing on it or pulling on it, and that's called work. So what we'll talk about now is transfer of energy. And there's two ways that we're going to be interested in. The first one is work. And that is energy transfer through a mechanical push or a pull. Okay, so I change the energy of something by pushing on it or pulling on it. And this will be given the letter W, what we described. It's also an energy. Going back to this system again, you see it has some energy. It's all potential energy right now. You'll notice that when I stretch this, I grab a hold of it. This is a simulation, but imagine you were doing it in real life. You'd have to stretch this thing, pull it down. Watch what happens to the bars as I pull it down. In particular, the total energy is changing, right? You're saying, wait a second, you said that the total energy of the universe was constant. How is the total energy changing? Because it's coming from the person that's stretching it. The person is expending energy and doing work on the system and increasing its energy. So as long as the extra person is pulling on this, can change the total energy, the person is transferring energy into the system, and so the energy of the system is changing. Once I let go of my mouse button, now the total energy doesn't change anymore because I'm no longer transferring energy into or out of the system. Okay? Let's consider a really simple example of a block on a table and analyze it from the point of view of conservation of energy. So initially, the block is sitting at rest on the table. This is going to be my initial situation. And so it's at rest. And then I'm going to act with some force. So I'm going to give the block a shove and let go. And you all know what will happen is that the block will slide a little ways across the table, but eventually come to rest. So it eventually will also end at rest. Finally, at rest as well. But in the middle, it has some motion, right? So how do I want to analyze this from the point of view of conservation of energy? First, I need to talk about what is the system. For me, the system is going to be the block and the table. And let's just for convenience, let's say that the block is at height h equals to 0. So let's just call this y equals to 0, so that I don't need to include any potential energy. So what do I have? Initially, I've got my kinetic energy initial is 0 because it's at rest. My potential energy initial is 0 because I said it's let's call it h equals to 0. And let's say that it has some initial internal energy, which I don't know. So Ui is something relating to the to the thermal energy of the system, which I don't know how to calculate at this point. And then eventually it comes to rest, and clearly its final kinetic energy is 0. Its final potential energy is 0. And how about its final internal energy, or its final thermal energy? We don't know it. Okay. Now the thermal energy final will be different than the initial thermal energy. How do I know that? Because I changed the system by acting with this force on it. So I added some energy into it. I did work on the system by acting with the force. So the change in the energy of the system has to be equal to the energy transferred in or out. And that's going to be the change in the kinetic energy plus the change in the potential energy plus the change in the thermal energy will be equal to the energy transferred in or out. In this case, if I look at the final and the initial, they both have 0 kinetic energy, so there's no change in kinetic energy. There's no change in potential energy. There is going to be a change in thermal energy, and it's going to be equal to the energy transferred in or out, and the energy was transferred by work. So in this case, my change in thermal energy, delta U, will be equal to the work done by that force, right? I don't know how to calculate the internal energy yet, but I know that whatever it is, it went up by a certain amount, and it had to go up by the exact same amount of energy that I put in by doing work, by pushing on the block. Okay? So delta U is equal to W. Delta U, change in energy, so that's U final minus U initial, is equal to the work done. Okay? All right, so that's a review of work. Now there's another way that I can transfer energy into the system, and that's heat. So what is heat? Heat is the transfer of energy through a temperature difference. From something hot to something cold. So for example, if you put your hand on a hot stove, you can get a burn. You can burn on your hand. You can see it, like physical damage to your hand. Clearly energy was transferred to your hand from the hot thing, the stove, into the cooler thing, your hand. Heat is given the variable Q. So work is W, heat is Q. Q is an energy transfer. So the units of Q are joules, same as before. And by the way, there's a small q, which is going to be the heat transfer divided by the number of moles, which of course the small q has units of joules per mole. Okay. So heat does not involve a push or a pull. The push or the pull is work, and heat is adding something adding energy or removing energy from a temperature difference from something hot to something cold. As an example, consider putting a container of water on the stove, and you can do the same thing. So I'll have my system here will be the water, and I can see that the temperature is going up because I put a thermometer in the water, and I can see that that is going to go up. So let's think about initial and final energies of the system. Okay, kinetic energy is 0 because remember, I'm using kinetic energy to talk about macroscopic motion. So I don't see the water moving as long as I don't boil it or anything. It's just staying there. And so I don't see any kinetic energy going on. And then maybe I call this y equals to 0, so I say it doesn't have any potential energy. So there's no potential energy here. But there is some internal energy initially, which I don't know how to calculate, and I don't know how to calculate it at the end either. But whatever it is, I know, because of conservation of energy, the change in kinetic energy plus the change in potential energy plus the change in internal energy is equal to the energy transferred. And how is energy being transferred here? Through heat, right? Energy is going from something hot to something cold, so the heat is coming in here, Q. And so I will have, in this case, these are 0, I'll have delta U is equal to Q. How much did the internal energy change? It changed by the exact amount of heat that was added to the system, that was transferred in. Okay, so this is the change UF minus UI. Change in thermal energy. And this Q is the heat added. By the way, there's another way I can increase the water's temperature, not by putting it on a stove. And this was figured out by James Joule. He did a famous experiment which kind of led to all these ideas. He found that if you put a water in a insulated tank and put a thermometer in it and had a paddle wheel where he cranked the paddle wheel so that it would stir the water, eventually the temperature of the water would rise. So in this case, the water is not being heated, its temperature is going up, but it's not being heated. This is work being done. Okay, so be sure that you understand the difference in work between heat and temperature. Okay, heat is a transfer of energy from something hot to something cold. That's not happening here. The water's temperature is going up, but it's not being heated. Work is being done on it. So in this case, I'm putting work in. It's going to go into kinetic energy because I'm going to see the water being stirred. I will be able to see that motion. Eventually, when I stop stirring it, the water will settle down and it will change into thermal energy. And I can see that with the thermometer that something has happened in the water to increase its temperature. Both cases, I changed the temperature of the water, but one was by doing work and one was by adding heat. So just to summarize, I've kind of given a big picture review of conservation of energy. The total amount of energy in the universe is constant, but I can change the energy of a piece of the universe by transferring energy in or out. There's two ways to transfer energy in or out for the purposes of this class. One is by pushing or pulling on the system, that's doing work on it. One is by adding heat, by putting it in contact with something hot. Or removing heat by putting it in contact with something cold. When I transfer energy into or out of the system, its total energy will change, and its total energy needs to include its kinetic energy, that's the bulk motion that I can see with my eye, potential energy, which we know has to do with like changes in height and changes in position, and its thermal energy, which can be measured with a thermometer that's related to temperature, and that's what we're going to get to a little bit more in this class. So I hope you have the concepts of what is work, what is heat, what is internal energy, or at least some starting to form those concepts. And we'll pick it up here and do some examples and some poll questions in class. I hope you found this useful, and see you then.